Good? Okay, sorry. Andrea Palermo introduced the concept of spin polarization earlier, so we'll be very fast. In heavy ion collision, basically, the two heavy nuclei collide, and they produce the quark-gluon plasma, which evolves freely, and then transition to a phase of hadron gas. And these hadrons reach the detector, which is actually what we observe. And from the properties of these hadrons, we can infer a lot of interesting things about the quark-gluon plasma. And in particular, one of the probe is the spin polarization of these hadrons. And so far, we know that, for instance, we know that assuming local thermodynamic equilibrium and hydrodynamic evolution and isothermal decoupling at very high energies, we are able to explain the theoretical and experimental observation of related with the spin polarization. These are all calculations made at local equilibrium. That is, there is no, we don't consider the effect of dissipation, which in principle can be important and very interesting. So what we want to do is basically extend this calculation, including the effect of entropy production, so dissipation. Okay. The point is, the quark-gluon plasma is assumed to be in local thermodynamic equilibrium, and we know which is the real state of the system, approximated state of the system for such quark-gluon plasma. It is given by this density operator here, rho, also called the Zubarev operator, which is calculated on this space-like hypersurface called the sigma equilibrium, which is the hypersurface where we assume that the quark-gluon plasma reaches the local thermodynamic equilibrium condition. After which, the quark-gluon plasma expand, does its things, and then at the freeze out, we have a transition from this quark-gluon plasma to a gas of free hadrons. So it's very useful. Here I ignore the presence of chemical potential in order to keep, let's say, the expression shorter. It is given that we observe the hadrons produced at the freeze out, it is useful to express the true density operator of the system not on the initial hypersurface, but rather on the freeze-out one. And so we can apply the Gauss theorem, and we see that the Zubarev operator, the statistical operator, is given by this expression, and is made by two terms. The first one is the local equilibrium expression calculated on the freeze-out hypersurface, and the second one instead is depends on the integral over omega. I didn't write what omega is. Is this a shaded gray region? Basically, it's the four volume inside between sigma freeze out and sigma equilibrium, which is related with dissipation. Now, once we have a statistical operator and we want to calculate the property of a system, we calculate the trace of this operator with any observable. So, I don't know, the energy densities, these kind of things. And this expectation value has two terms, the local equilibrium one and the dissipative one. This one has been studied a lot in literature, and it is able to reproduce the properties of the local and global spin polarization of fermions. However, this term is often overlooked. And so what we are going to do now is to see what happens when we study this contribution rather than the green one. The idea is to apply linear response theory to this term, and if we calculate the expectation value of any observable O, the general expression is the following. Now, it's a little bit involved, but it's quite simple. We see that there is two dependencies. The first one is dependencies of the coordinate y, which is the coordinate that parameterize the volume of the quark-gluon plasma, and the thermodynamic gradient. Also, we have the dependence on the stress energy tensor calculated on this volume, while there is another coordinate x, which is the space-time point where we calculate this observable. And this is the homogeneous equilibrium operator. The linear response theory basically assumes that dissipative correction are small correction around the equilibrium. So this is why we have this simplified formula. And these are something very well known. For instance, if we consider the case of the stress energy tensor as observable, we find that the dissipative correction is given by these terms here, which is a very well-known expression. And we see that, as I said, the expectation value is calculated at equilibrium, okay? Because linear response theory assumes small correction around the equilibrium. Now, what we do usually to compute the dissipative terms, we assume that there is a clear separation of scales. basically this is the assumption of hydrodynamic regime. So the gradient of the thermodynamic field varies over macroscopic lengths, wherever instead this quantum correlator is different from 0 only if y minus x is a microscopic length. That is that when this correlator is different from 0, the gradient is almost constant. So by this assumption, what is usually done in literature is, okay, we just take the gradient outside from the integral, and then we obtain the famous Kubo formula. Actually, this is the Kubo formula, but often this is called the Kubo formula, that tells us that the dissipation in x is directly proportional to the thermodynamic gradient on x times a viscous coefficient. So this is a very important point, because we will not do the same thing, actually. Now, what we want to do is, okay, this defines the concept of dissipative correction. We want to calculate the spin polarization vector, the dissipative correction to the spin polarization vector. And to do so, the idea is to use the relation that links the spin polarization vector with the Wigner function. Basically, this function here allows us to write the spin polarization vector of fermions produced at the freeze-out in terms of this integral. And this is the relation that links the Wigner function to the spin polarization vector. So if we calculate the dissipative correction to the Wigner function, we obtain basically the dissipative correction to the spin polarization vector, according to this formula. This is the axial part of the Wigner function. So this is the very simple idea behind this work. We calculate the dissipative correction of the Wigner function, and by this formula, we immediately obtain the dissipative correction to the spin polarization vector. So let's see. As I said, this is the geometry of our problem, and this is simply the formula I showed you before with O, that in this case is the Wigner function. A and B are Dirac indexes. Now, the situation is the following. We calculate this Wigner function at the freeze-out hypersurface, because we observe, as I said, the hadrons produced at the freeze-out. And on the freeze-out, the dominant degrees of freedom of the system are those of quasi-free hadrons. Instead, in this omega volume, this gray shaded region, characterized by the coordinate y, T mu nu, the stress energy tensor, is the stress energy tensor of the coupled quark-gluon plasma, which we actually have no idea how it is made. So the important point is that given that the Wigner function is calculated at the freeze-out, we can use the free expansion, the free field expansion for the Wigner function to plug inside here, while this cannot be done for the stress energy tensor. The stress energy tensor will depend by all the possible interactions, so it will be very complicated. Now, the result that we find, that I will show you, is that the Wigner function is not only a function of the x, but is also a function of the momenta k. And what we find is that this correlator, which appears in the formula, actually is different from 0 not only on a small point, but on a k-dependent word line, which, so on an infinite points, a line, which depends on the momenta itself. So this means that on this line, the gradient actually may vary significantly. So the idea that okay, the correlator is almost 0 when the gradient varies, and so we can take out the gradient, doesn't apply for the Wigner function. And thus, the usual expression of the Kubo formula cannot be used for the Wigner function. It is not true that the dissipative correction to the Wigner function is directly proportional to the gradient in the same space-time point. To see this, we rewrite in a different way the dissipative correction to W. This is just a clever way to rewrite the correction. And it's clever why? Because instead of working with the pi and pi prime, which are the momenta of the Wigner function, we work with q and k. In particular, we are able to factorize all the dependence on the coordinate of the volume outside the interaction term. So this is the only part that actually depends on the coordinate of the volume. The interaction, the correlator, is inside this f mu nu, which I express here. And so basically, all the information about interaction is now a thermostatic thing. T mu nu is calculated in a 0 point, in some sense. And this is the only term that contains the interaction. So basically, we separated the y dependence from the interaction dependence. This is important because we have to check that separation of scale that I told you before. And also, this delta function here constraint q. So this is not a 4-dimensional integral over q, but is rather a 3-dimensional integral over q, because the time component of q is dependent on the space component of q and k. And this is important for the following. So we come now to the problem. Okay, so far we just wrote in a clever way, let's say, the dissipative correction, but we have no idea of how the interaction term is made. So we started to try to analyze this interaction term, and the idea that we had is we can expand this expectation value in a base of the in components of the Clifford algebra. So in principle, this thing here depends on this tensor, gamma mu nu, which is expanded on the identity, the vector part, the tensor part, the pseudo-scalar part, and the pseudo-vector part. And each of these tensors here are built with all the vectors that we have at our disposal. K, Q, this because P and pi prime are actually related with K and Q. Beta, because this is a thermal expectation value. And also we have the possibility to have a dependence from this pseudo-vector. Also, these gammas will depend on any possible scalars that we can build with the things that we have at our disposal. But we can have any pseudo-scalars. So this expansion here, for instance, gives us the following expansion for gamma mu nu. So we have K mu, K nu, Q, Q, beta, beta, and so on and so forth. And for each tensor structure, we have a function, a scalar function, which we call the form factor, which contain all the information about the interaction. So this method seems not that clever, because if one start to count any possible term, we end with almost 300 possible scalar functions, which of course is crazy. But the idea is that we can reduce a lot of these terms. So we actually know the tensor structure of this expectation value, and all the ignorance about the interaction is only inside these scalar functions here. We have a different way to reduce this number, which I assure you is a long work, but it has been done. We can impose the Dirac equation, the transverse condition to the expectation value. Also, we have some thermostatic conditions, such as this, let's say, KMS condition. And also, we can impose some relation dictated by parity and time reversal transformation. All in all, we can show that in the end, only only this tensor here is the one that actually contributed to this expectation value. All the other ones are actually dependent from this. We can write them in terms of this one. And in this expectation value, I counted as, in principle, 92 form factors, only this gamma, but the independent form factors are only 14. And I see this as a big success, because we reduced the number of the possible terms from more than 300 to only 14. So all the information about the interaction, which is completely unknown, is inside these 14 functions. I didn't write all of them because it's very long. Now, this was for the interaction. What about the problem I told you before, which is the main point of the work? Well, let's return now to the dissipative correction of the Wigner function. This is the formula I've shown you. Now, suppose that the integral here is peaked around epsilon. This is y minus x equal to 0. If it is peaked in y minus x equal to 0, the idea is that, okay, basically we can extract this gradient out from the integral, compute it in x, and we are left with something that is just a viscous coefficient written in a different way. So the correction will be, again, proportional to the gradient in the same point times a viscous coefficient. This is not the case, however, because given the condition that we have on Q, actually this exponential has the following form. And we can see that this actually vanish not only in a y equal x, but on a word line, different from every possible y, dependent on k. So the idea that we can't just take the gradient out and say, okay, we computed it in x, and everything left is a viscous coefficient, doesn't apply for the Wigner function, at least for the free Wigner function. So this assumption doesn't apply. So the problem is much more complicated, because now we have to basically integrate the gradient with all the interaction terms. So the hypothesis that we can just say gradient times viscous coefficient is wrong. And this is why we actually expanded in all these form factors, because in principle they all contribute in a different way once integrated over Q and over Y. Of course, we actually don't know how these form factors are made. And I conclude. So this is, of course, still a work in progress, but we found that the usual assumption that we can compute dissipative correction as gradient times the gradient of the same space-time point times a viscous coefficient doesn't apply for the Wigner function, and so doesn't apply for the spin polarization vector. So in order to compute dissipative correction to the spin polarization vector, much work is needed to be done, and is what we are actually doing now. Thank you.
Okay. So good morning, everybody. First of all, I would like to thank the organizers for letting me be here and presenting my work on advancing of semi-classical formulation of spin hydrodynamics, which I have been doing in collaborations with people of my group in Frankfurt, David Wagner, Masoud Shokri, Julia Sammet, and my advisor Dirk Rischke. So first of all, I would like to start with the outline of my talk. I would like to introduce some motivation where we caring about spin hydrodynamics, which benefits we can get from a semi-classical approach to this theory, and then I will try to present some applications and result, and then summarize our work and look for some possible outlooks. So first of all, just to put everybody on the same page, we have already been hearing extensively from the previous talks about the importance and the effects of what happens in non-central heavy ion collisions where we have two heavy nuclei carrying a large orbital angular momentum, part of which is transferred to the fermating quark-gluon plasma, which will be a result and measured experimentally in the polarization of the final products. So essentially, if we consider only the global polarization, meaning the integrated one along the angular momentum direction, what we see is that this can be theoretically explained by only equilibrium effects. So the spin degrees of freedom are assumed in equilibrium, encoded in the spin potential, which tends to equilibrium values given by the thermal vorticity, and this is analogous to the well-known Barner effect when we have some polarization of a ferromagnet, which is undergoes on some rotation. However, when we consider the angular dependence of this polarization, namely the local polarization, what we can have is that we are not able to only theoretically explain these effects by only including equilibrium parameters, but we have to actually invoke the shear viscosity, so a non-equilibrium term, in order to theoretically explain the data from the experiment, as you can see in this plot. So the question arising from this problem is actually how can we take care of the equilibration and in general to the dynamics of these spin degrees of freedom towards their equilibrium value. In order to give an answer to this problem, we developed this theory of spin hydrodynamics, which is based as the usual theory of hydrodynamics on conservation laws. So for an uncharged fluid, we have the conservation of T mu, the energy momentum tensor, and we refer to spin hydrodynamics when we also include the separate conservation of the total angular momentum as an independently conserved charge, that here it has been presented as a current in order to promote our theory to a covariant theory, in which we can split this current into this orbital part and this spin part, which has been rewritten in terms of these Killing vectors k nu that are actually the generators of rotations. And this allows us to actually enable a covariance when we take care of coordinate transformations even in flat space-time. So when we then plug the first conservation equation into the second one, what we can have is actually a dynamical equation taking care of the evolution of the spin degrees of freedom, which depend on the antisymmetric part of the energy momentum tensor. So if we take a closer look to our equations, what we have is a total of 4 plus 6 equations, while the things we don't know, they are a total of 16 plus 24. So it is clear that we are lacking of some information that we can systematically extract by taking a look on the underlying microscopic physics, and namely starting from quantum field theory and then deriving from that the quantum kinetic approach that will lead towards the method of moments to our hydrodynamics. What is semi-classical spin hydrodynamics? Is essentially a simple set of 3 main assumptions where we can actually simplify and construct our framework. The first one is actually assuming that the spin, being a quantum effect, we can theoretically describe it as the spin tensor being a small one. So we can actually parameterize this as putting an h-bar factor in front of our usual spin tensor. The second assumption that we make is that the spin is an independently conserved charge when we are in a global thermodynamic equilibrium state. And then the third one is actually that we can parameterize our energy momentum tensor as not having any contribution at the linear order in h-bar. And moreover, the antisymmetric part of this energy momentum tensor only takes into account contribution up to the second order in the same constant. So these are actually these only 3 assumptions, and these are based on, as I was saying, like underlying microscopic physics, so a quantum kinetic framework developed by Nora Vikenant in this paper. Here I have also reported the general form of the antisymmetric part of the T mu nu, essentially where we can assume to actually decompose it into an electric and magnetic component and taking into account some dissipative contribution parameterized by gamma A's. And all these gamma factors, they are just function of our fluid variables. So what's the gain from this semi-classical spin hydrodynamics theory? If we consider our general approach in describing a theoretical description of heavy ion collisions, we will have, after a pre-hydrodynamic stage, we would have to take into account, for considering the dynamics of spin degrees of freedom, this set of coupled equation of motion, which is very challenging to understand, in order to then extract some results to compare to the data. While if we adopt the assumptions that I have just listed in the previous slide, what we can do is that considering just the standard hydrodynamics, which is actually the conservation of the symmetric part of T mu nu up to the order h bar square, and then to use it, the standard hydrodynamic, as an input for solving the spin dynamics. And then from that extract some data for some prediction for our data. So the gain from this theory is actually a real decoupling between the fluid part, the fluid dynamics, and what can be used as an input for the spin dynamics, which can be solved on top of these standard hydrodynamic solutions. And in order for provide you with some examples, I've been listing here 3 simple solutions of standard hydrodynamics that we can explore to see to have a setup to solve the equation of spin dynamics. So first of all, I would like to start with some hydrostatics, which is the most simple setup that we can think about, and then move to some linear hydrodynamics and also investigate some nonlinear perspectives within the Bjorken background. Just a small remark, as you may have noticed, when we consider then the equations, the dynamical equations for the spin degrees of freedom, we would have a total of 6 equations for 24 unknowns, and we can split the spin tensor in an ideal part and a dissipative part. So what we will be referring to is this ideal spin hydrodynamics, whose name can be a little bit misleading, but what we mean by that is actually only taking into account the ideal spin part of the spin tensor, and actually neglecting some dissipative effects of spin. By making this choice, we can actually have a total of 6 equations for only 6 unknowns, which are like the components encoded within our spin potential. Thanks to this, we can also, based on some symmetries, find a final form of the ideal part of our spin tensor, where this constant that we're saying like are actually functions of our fluid variables that are constrained within quantum kinetic theory. So now we have all the elements for essentially write down these dynamical equations, and this is the general form, how they look like. So they are essentially these relaxation type equations for respectively the electric and magnetic component of the spin potential, and this is how they present, involving all the contributions for gradients of fluid variables. And especially what we can see is that it is clear that there is for both of them a source term, and that they will essentially evolve towards the expected equilibrium value, namely the acceleration and the fluid vorticity. So let me start for the first solution is essentially hydrostatic, when we neglect the gradients of temperature and velocity of the fluid, and then what we can do is actually come and reduce the previous complicated equations to a very simple set of equations that are presented here, and then by performing a Fourier transformation, what we can derive is that we can derive as a damping of a damping of spin waves, as we can see here, with this damping factor arising from the presence of a non-vanishing part of the antisymmetric contribution in the energy momentum tensor. So the spin degrees of freedom, they evolved towards with these damped spin waves. So this was, of course, the most the easiest setup that we could think about, and then we can, as a further step, think about investigating small perturbation of our system, and so taking into account this linear spin hydrodynamics when we consider linear perturbation of our quantities around their equilibrium values. So the equations now will appear as this on the top. And of course we can perform again like a Fourier transformation, and then we will have, by plugging into this the fluid degrees of freedom, we will have the equation of motion that will be written like this. And then for the fin spills, as I said, we will have also the spin part and the back reaction from the fluid. So if we think about putting this in a metric form, what we can see is that we will have to solve the system when now the total matrix that it's taken into account the evolution of both the fluid and the spin degrees of freedom is now a triangular matrix, which we can think about solving with the characteristic method. And once again, we can see that due to this triangular form with no back reaction of the spin to the fluid, what we can have is that again we can decouple the fluid dynamics and the fluid dynamics solving separately the determinant of the matrices equal to 0. So what we can actually gain from that is that again we don't have any influence from the fluid perturbations on the spin waves, and we would have the same relaxation time scales as the previous setup that have been showing. Finally we can move to a slightly more complicated setup, and taking into account this toy model given by the conformal Bjorken background, where we assumed still vanishing thermal vorticity. And what we have is that, of course, we have a metric in terms of the mean coordinate, and we impose the covariance, the conformal invariance, which will be constrained by these two constraints that we only require at classical level. So actually they have been realized within this semi-classical approximation. And what we can see is that this is the way how we can present respectively the fluid sector and the spin sector, which are the only ways allowed by conform Bjorken symmetries. And without going into the details of the calculations, if we express everything in terms of this thermal time, and we enable us to use the attractor solution for the fluid sector, what we can show is that this late time behavior solution of the components of the spin potential, which will then be relaxing as the previous cases in these equilibrium values, which in this case is again 0 because we haven't turned on the thermal vorticity. So again, we will have the same relaxation times, Tk and the omega, that are governing the equilibration of the spin degrees of freedom as shown in the previous backgrounds. So just to summarize and have a better picture of the time scales of hydrodynamics, what we can see is that essentially in this picture we can represent the relaxation times of the spin of the components of the spin potential as scaled within the relaxation time of the shear stress tensor, so the fluid variables. And what we can see is that we have a discrepancy when we take into account the dependence with respect to Z, which is the ratio of the mass of the particles as compared to the temperatures. So what we can see is that if we take a look on the high energy regime, what we can see is that these time scales, they are essentially comparable. So in a sense, we are allowed to neglect the equilibration dynamics of the spin degrees of freedom, while actually if we move and go to low energy heavy ion collisions, what we can have is that the time relaxation time of the magnetic component blows up and might become also larger than the lifetime of the fireball itself. And this is basically telling us that we shouldn't neglect the equilibration dynamics of the spin degrees of freedom. So this is actually the take-home message. I just want here to let you know that we are still improving our setups, because these were just very simplified solutions, and what we are trying to do is actually considering a rigidly rotating fluid where essentially we will have a non-vanishing contribution from the thermal vorticity, and what we actually expect to see is essentially to see this equilibration of the components towards respectively the acceleration and the fluid vorticity. But we are, when solving this system, we are also solving for all the components, all the 6 components which are decomposed into this tetrad that I've been showing here. So we would have a total of set of equation of motion for 6 different the components of K and omega. And what we expect is that despite this equilibration of the components with a source term, we would expect that if we stop our measurement at some earlier time, we would have some unexpected polarization patterns given by some transient component that then will relax eventually to 0. So this brings me to my summary. So as we have seen, the spin hydrodynamics is in this semi-classical approach is a powerful tool for investigating these polarization patterns in different backgrounds, and of course we are trying to implement it to more realistic ones. And the take-home message is that this spin dynamics becomes particularly relevant when we consider low energy heavy ion collisions. And regarding the outlook, besides, as I said, considering more realistic setups, we are also considering the inclusion of external background fields like electromagnetic and gravity-induced effects, and also considering some numerical results that are actually representing the data. And with this, I thank you very much.
Thank you very much. Kenji?
Okay, so it is very nice to see that such uncertainty is constrained in this way. But my question is actually more fundamental level. I mean, you talked about electric and magnetic component, but electric means that is a boost operator, the generator of a spin part, right? And then it is not Hermitian, which means that it cannot be a physical observable, in my opinion. And so in your notation, the kappa. So what is the physical interpretation of kappa? Kappa should not be the physical observer in my sense. And also, if you adopt the completely anti-symmetrized form of a spin tensor, then of course such electric component is automatically zero. And only the spatial rotation makes sense. So
can you repeat the second part, because I think I didn't get the second part.
I'm asking about only one thing. Okay. So the electric component is not really the physical observable because it is related to the boost generator, and that is not Hermitian. So it is
Yes.
Anything that is not Hermitian cannot be the physical observable, in my opinion. So the kappa cannot be the hydro variable in my
But I think
in
from
my
a
opinion.
mathematical point of view, what we were interested into is actually whether to consider the dynamics of the evolution of these spin degrees of freedom, just to investigate some data without considering that these
Okay,
are
so this is related to the choice of S mu nu over omega mu nu. Okay, so if or the spin tensor is originally the 3-rank tensor, right? And
Yes.
so that zeroth component is a spin. And so if you consider the completely anti-symmetrized form, then the S00I is automatically 0. But of course, if you break such kind of the symmetry, then of course 00I is a boost generator. Yes. But there is no physical observer, no conserved charge corresponding to the boost, right? If you see the spin part only. The spatial derivative part is a different thing because it has actually the infinite dimensional representation. Then Hermitian representation is possible. But spin is a finite dimensional representation. Then there is no such representation of a Lorentz group. That is well known. Anyway, so.
Thank you for
Yeah.
the comment. Thank you for the comment. I think this is just like some theoretical investigation on the relevance of the spin degrees of freedom and equilibration, but it didn't have to have 1+1 like comparison with data. Yeah, sure.
Fortunately, we're kind of running a little bit late, so let's thank the speaker. Remember that we have a discussion session in the afternoon for people who have an extra question to ask. And the next speaker is lunch. Yeah. It's a very popular speaker.